So when you're solving a system of ODEs like this, where A, B, C, D are all constants, you end up with different phase portraits. There are only so many different types of phase portraits you can get. It would be really nice to be able to classify them, make a nice plot of it. And so that's what this is going to be about. And it turns out the determinant of your coefficient matrix A and the trace of A are really useful to plot out the different regions where all the different types of phase portraits occur, like saddles and nodes and spirals and centers and degenerate nodes and stars and all that fun stuff. So let's go ahead and dive right in. So first let's write the determinant of A. Well, that's AD minus BC. We have the trace of A. Oops. That's the sum along the diagonal of a matrix, so that's going to be A plus D for us. And they actually end up having very nice relationships to the eigenvalues. Now, one way we can do that is when you're computing the eigenvalues, right, you form that polynomial. It's, right, you subtract the lambda times I, determinant equals 0, so you have A minus lambda times D minus lambda minus B times C. So that equals 0 for these symbols to be eigenvalues. If you multiply that out, you end up with, oops, lambda squared plus, I'll do minus, right, minus A plus D times lambda, oops, plus AD minus BC. Equals 0. Well, that's kind of nice because the trace is occurring right here, and there's the determinant. So, but what if we knew the roots, lambda 1 and lambda 2, and we expanded that polynomial? So we have lambda minus lambda 1 times lambda minus lambda 2 also equals 0 if we know the roots. So if we expand that out, we'll get lambda squared minus lambda 1 plus lambda, oops, that's kind of a plus, plus lambda 2 times lambda plus lambda 1 times lambda 2 equals 0. So now if we match these up, I've got 1 times lambda squared on both of them. But here I have minus, here's lambda 1 plus lambda 2, here's A plus D times lambda, so the coefficient in front of the both the lambdas. Then the constant term I have here lambda 1 times lambda 2, and here I have AD minus BC. So then using that, the coefficients have to match. So you actually have the determinant of A has to equal lambda 1 times lambda 2. And you have to have the trace of A has to equal lambda 1 plus lambda 2. So the trace and the determinants have a really nice relationship. And we can use it to classify what kind of phase portrait we're going to get based on the trace and determinant. All right. So let's start out with kind of the easy one. If we want a saddle, in order to form a saddle, you have to have a positive eigenvalue and a negative eigenvalue. All right, so saddle, that means lambda 1 is less than 0, less than lambda 2. And I've written it here because if you have one eigenvalue is positive, one eigenvalue is negative, you're always going to have the determinant is negative. Positive number times negative number gives you a negative number. So the saddles are actually all, and I'm going to leave a little room for myself, all down here. All right, so that covered about half of it. So now let's think, okay, what about spirals and what about nodes? Actually, let's look first, what about stable versus unstable? So if something is stable, then we're going to have two negative eigenvalues. If something is unstable, we're going to have two positive eigenvalues. If it's imaginary, then the real part will be negative, will be stable, positive will be unstable. So then we have the determinants, that's not very helpful. If they're both positive or both negative, the determinant doesn't help us. But here, if they're both positive versus both negative, or if it's complex roots, the complex conjugates, the imaginary part will cancel out. We still have positive real part and negative real part in both. And so the trace will actually help us determine whether something's stable or unstable on the top half. And so if the trace is negative on the top half, then we're going to have stable. And so negative trace is over here, so this is the stable half. And then if the trace is positive, we're going to have unstable. So trace is positive over here, so this is the unstable half. So everything in this quadrant will be stable, everything in this quadrant will be unstable, everything down here is a saddle. All right, well, okay, so now let's try and think. There's nodes and there's spirals. Let's see, how we determine whether we have a node or a spiral. So the biggest difference is on spirals, we have complex roots. On nodes, we don't have complex roots. And so let's actually look at solving for the roots here. So we've got this polynomial we've got to solve for. We can use the quadratic formula. So we should have lambda 1 comma lambda 2, we're going to get it from the plus minus, equals, all right, so I've got my negative coefficient on the lambda to the first power. So I end up with a negative a plus d. So negative a plus d plus or minus square root. I'm going to have b squared, so a plus d squared, minus 4 times the coefficient on lambda squared, so just 1, times the constant coefficient, so the AD minus BC. All over 2 times the lambda squared coefficient, so just 2. All right, so we want to know if something is going to come out, excuse me, complex versus not complex. Well, if we're going to have complex, then that's all going to be determined by whether or not the inside of the square root is positive or negative. So I can actually rewrite this. So I have a plus d squared. Well, that's the trace squared, right? Trace of a squared, and then minus 4, that's the determinant of a. And I've got a couple things that could occur. So I could have this thing be greater than 0, or I could have it less than 0. Let's not worry about the equals 0 case right now. If the inside of the square root is positive, then lambda 1 comma lambda 2 are real. So we're going to end up with nodes. If the inside of the square root is negative, we're going to have lambda 1 comma lambda 2 are complex. So we'll end up with spirals, and I'm forgetting about the other cases right now, the edge cases. So, okay, well, the boundary then is in between. If I have the trace of a squared minus 4 times the determinant of a equal to 0, that should separate out the spirals from the nodes. So that's a parabola. So that's going to look something like that. So the equation of this line is trace of a squared equals 4 determinant of a. And then keeping careful track of less than greater than, inside of here we're going to have spirals. Inside the parabola we'll have spirals. And spirals here. And then stable spirals, unstable spirals. But I've kind of left out, what happens on the axis right now. So if we're on the axis, we have complex, but if we're on the axis, the trace of A is going to be 0 there, right? That's the definition. So if we have complex eigenvalues and the trace of A is 0, that means the real part is 0, right? So we have 0 plus some imaginary component, then 0 minus the imaginary component. That's going to cancel to 0. So actually on this axis here, we're going to have centers. Which kind of makes sense. You have centers separating stable spirals from unstable spirals. All right, now I forgot to label the nodes. So if we're outside the parabola, then we're going to have nodes. Gotta leave myself room. And again, so stable nodes, unstable nodes. All right, I have a couple edge cases left. So one of the easier edge cases is the non-isolated fixed points. So that one's going to occur when we have one non-zero eigenvalue and one zero eigenvalue. All right? So if one of the eigenvalues is 0, then the determinant is going to be 0. All right? And then if one of the eigenvalues is 0, then the trace will be positive if lambda 1 is positive, the trace will be negative if lambda 1 is negative. So assuming lambda 2 was the 0, 1. So that's actually all occurring on the x-axis. So I think I have room here. On the trace of a axis, I should say. Non-isolated fixed points. And then it's occurring on both sides. It's the entire trace axis. So stable non-isolated fixed points here, unstable non-isolated fixed points here. All right, well, we're still missing a few. So we've got the silly case in the middle, and I think I'll do that here. So right in the middle, we kind of have the silliest case here, which is the constant solutions. The only way to get that point is if the entire coefficient matrix is all zeros. Then you get lambda 1 equals lambda 2 equals 0. So that's the silly one. What about stars and degenerate nodes? What kind of process of elimination? We know they should occur on this parabola. Let's take a look. So for a star, we need lambda 1 to equal lambda 2. And then we get lambda 1 to equal lambda 2 if we have the the square root part, plus or minus be 0. So we're going to end up with, running out of room here. We're going to have stars for sure here. And then it turns out we're also going to have degenerate nodes. Those also have eigenvalue with multiplicity 2. And I'll put an and, why not? All right, then this half of the parabola is unstable stars, unstable degenerate nodes. This half of the parabola is stable stars, stable degenerate nodes. So there you go. This is called a Poincare diagram. This is a spot. I think it goes that way. I'm not sure about that. Oh, there's an accent on the E. Gonna go with that. Don't quote me on that. But yeah, so this is a way to classify them. And one thing to note though is the matrix A is in 4-dimensional space, right? We have 4 parameters we can choose. We can choose a number for A, a number for B, a number for C, a number for D. But on this thing, it's 2-dimensional. So you're taking 4-dimensional space, mapping it to 2-dimensional space in this Poincare diagram. And so what can end up happening is you can actually have the exact same point correspond to a bunch of different matrices. So at the exact same point, you can actually have a star or a degenerate node, and it can have the same determinant, same trace. But there you go. So the next thing is, well, we have all these different phase portraits, and now if we start changing parameters, we should be able to kind of transition smoothly from one type of phase portrait to another. So I've made a nice little animation showing that and what's happening to the matrices and the solutions and the phase portraits as that stuff is changing.